Welcome to Part 3, NVIDIA Deployment in Service Chain. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. In Part 2, we built the infrastructure foundation, VNets, subnets, and route tables. But right now, our spoke traffic is being routed to non-existent firewall IPs, creating black holes. Today, we fix that by deploying network virtual appliances and establishing VNet peering to complete our service chain. This is where everything comes together. We'll deploy firewall and IDS/IPS NVAs, configure them for IP forwarding, establish peering connections between hub and spokes, and finally associate our remaining route tables. By the end, you'll see traffic flowing through the complete service chain. I'll show you both marketplace NVIDIA deployment and custom Linux-based NVAs for those who want to experiment without licensing costs. The principles apply regardless of which NVIDIA vendor you choose: Palo Alto, Checkpoint, Fortinet, or even Azure Firewall. We'll also test our configuration at each step, so you can see exactly when traffic starts flowing and how to verify the service chain is working correctly. This hands-on validation is crucial for building confidence in your deployment. Let's start by creating the network security groups that will protect our NVAs. Creating network security groups for NVAs. Before deploying NVAs, we need network security groups to control traffic to and from these critical security appliances. NSGs act as distributed firewalls at the subnet or NIC level, providing an additional layer of security. For the firewall NSG, we're allowing inbound traffic from spoke networks, such as 10.2.0.0/16, 10.3.0.0/16, and 10.4.0.0/16. This is the traffic that our route tables will send to the firewall. We also allow traffic from other hub subnets for management and chaining purposes. Port 443 for HTTPS and port 22 for SSH are allowed from the management subnet only. This restricts administrative access to jump boxes in the management subnet, which is a security best practice. Never expose management ports directly to the internet. The priority values, 100, 110, and 120, determine the order of rule evaluation. Lower numbers are evaluated first. I always leave gaps between priorities, for example, using 100 and 110, instead of 100 and 101. This allows you to insert new rules later without renumbering. For the IDS NSG, we follow a similar pattern, but we allow traffic from the firewall subnet, since that's where inspected traffic originates. The IDS only receives traffic that has already passed firewall policies, so its NSG can be more permissive for internal traffic. Notice we're not explicitly defining outbound rules. By default, NSGs allow all outbound traffic. For production environments, you might want to restrict outbound traffic too, but that adds complexity we'll avoid for now. These NSGs provide defense in depth. Even if someone misconfigures routing, the NSGs prevent unauthorized access to your NVAs. It's a crucial security layer that many deployments overlook. Deploying the firewall NVA. Now for the exciting part, deploying our first NVA. I'll show you how to deploy a Linux-based virtual machine that we'll configure as a firewall. This approach lets you experiment without expensive licenses, though the same principles apply to commercial NVAs. First, we create a public IP for management access. In production, you might skip this and access NVAs only through the management subnet, but for initial setup and learning, direct access is helpful. The standard SKU supports availability zones and static allocation. For the virtual machine, I'm using Ubuntu 20.04 LTS with a standard DS3v2 size. This gives us 4 vCPUs and 14 GB of RAM, enough for moderate traffic loads. For production, size based on your throughput requirements. Remember, NVAs can become bottlenecks if undersized. The critical parameter is private IP address 10.1.2.4. This must match the IP in our route tables. If this IP changes, all routing breaks. Always use static IPs for NVAs. I've seen dynamic IPs cause overnight outages when virtual machines restart and get new IPs. Authentication can be password or SSH key. For production, always use SSH keys. I'm showing password for simplicity, but please use keys in real deployments. Store credentials securely. Azure Key Vault is ideal. The NSG Firewall NSG parameter attaches our network security group. This takes effect immediately, so management access is restricted to allowed sources. Once deployed, this virtual machine will receive all traffic from spoke networks. But it won't forward anything yet. We need to enable IP forwarding at both the Azure and OS levels. That's coming next. Deploying the IDS/IPS NVA. The IDS/IPS deployment follows the same pattern as the firewall, but with a different IP address that matches our route tables. This second NVA in our chain provides deep packet inspection capabilities. Again, we create a public IP for initial management access. In mature deployments, you might have only internal IPs and access these NVAs through a bastion host or a VPN, but for setup and troubleshooting, direct access is valuable. The VM configuration is identical to the firewall. Ubuntu 2004 LTS, standard DS3v2 size. In production, your IDS might need more resources than your firewall, especially if performing SSL inspection or complex pattern matching. Size appropriately based on your inspection needs. The critical static IP is 10.1.3.4, matching our route table configurations. The IDS will receive traffic from the firewall at this address. Remember, this IP is hard-coded in multiple route tables, so it cannot change. For a real IDS deployment, you would install software like Snort, Suricata, or a commercial solution. These tools can inspect traffic for malware, intrusion attempts, and data exfiltration. For our lab, we will just configure basic forwarding to prove the chain works. The beauty of this architecture is its flexibility. You can swap these Linux virtual machines for any commercial NVA. The routing doesn't care what appliance you use, as long as it forwards traffic correctly. After deployment, we will have 2 NVAs ready for configuration. But they are not yet forwarding traffic. That requires enabling IP forwarding, which we will do next. Enabling IP forwarding is the most critical step, and it's one that many people miss. IP forwarding must be enabled at 2 levels: at the Azure NIC level, and within the operating system. If you miss either one, your NVAs become black holes that receive traffic but don't forward it. At the Azure level, setting IP forwarding to true tells Azure's SDN layer to accept packets that aren't destined for this NIC's IP address. By default, Azure drops such packets as a security measure. For an NVA that needs to forward traffic between networks, this default behavior must be overridden. The NIC update command modifies the existing NIC configuration. This change takes effect immediately, with no reboot required. You can verify this setting in the portal under the NIC properties. Inside the Linux virtual machine, we also need to enable IP forwarding in the kernel. The command to write the number 1 into the file at /proc/sys/net/ipv4/IP forward will enable it temporarily. For persistence across reboots, we modify the file at /etc/sys/control.conference to include the line net.ipv4.IP forward equals 1. The IP tables rules I'm showing implement basic forwarding with connection tracking. The forward chain rules allow established connections and new connections from spoke networks. The NAT rules aren't needed for basic forwarding but would be required for internet egress scenarios. For production Linux-based NVAs, you would implement much more sophisticated IP tables rules, perhaps integrating with fail-to-ban, implementing rate limiting, or adding application layer filtering. Commercial NBAs handle this through their own management interfaces. Here's a common troubleshooting tip. If traffic reaches your NBA but doesn't leave, check IP forwarding first. Use TCP dump on the NBA to see packets arriving and departing. If packets are arriving but not leaving, IP forwarding is usually the culprit. VNet peering is what connects our isolated VNets, allowing traffic to flow between them. Without peering, even with correct routing, traffic cannot leave its source VNet. Let's establish these connections, starting with hub-to-spoke peering. The peering relationship requires configuration on both sides. Think of it as a handshake. We start with the hub side, configuring 3 separate peerings to each spoke. Each peering is independent. You can add or remove spokes without affecting others. The Allow VNet Access parameter enables basic connectivity between VNets. Without this, the peering exists but no traffic flows, which is useful for staged deployments where you want to prepare peering before enabling traffic. The Allow Forwarded Traffic parameter is crucial for our NVIA scenario. It allows traffic that didn't originate in the source VNet to traverse the peering. Without this, our NVAs couldn't forward traffic between spokes or to on-premises. This parameter is often missed, causing forwarding failures. We're not using the Allow Gateway Transit parameter yet because we haven't deployed the VPN gateway. That comes in Part 4. For now, we're focused on getting the service chain working for inter-VNet traffic. Notice the naming convention. Hub to Spoke 1, Hub to Spoke 2. Clear naming helps enormously when troubleshooting. In the portal, you'll see these peering connections from the hub's perspective. After creating the hub side peering, the connection shows as initiated until the spoke side is configured. It's a two-way handshake. Both sides must agree to peer. Creating VNet peering from the spokes to the hub. Now we complete the peering handshake from the spoke side. Each spoke needs to peer back to the hub, accepting the connection initiated from the hub side. This bidirectional configuration is what enables actual traffic flow. The spoke side peering uses the same parameters as the hub side. Allow VNet access and allow forwarded traffic. Both sides must agree on these settings for traffic to flow correctly. We're not setting use remote gateways yet because the VPN gateway doesn't exist. Attempting to set this parameter now would fail with an error. This parameter will be added in Part 4 when we configure gateway transit. After configuring both sides, the peering status changes from initiated to connected. This status is visible in the portal and CLI. Connected status means traffic can flow between the VNets, subject to routing and NSG rules. With peering established, our architecture transforms. The isolated VNet islands are now connected through the hub. Traffic from any spoke can reach any other spoke, but only by traversing the hub, which is exactly what we want for security inspection. For common troubleshooting, if the peering shows initiated and not connected, check that both sides are configured. If the status is connected but traffic doesn't flow, check that Allow Forwarded Traffic is enabled on both sides. NSGs and routing are the next places to check. The beauty of this hub and spoke topology is its scalability. Need a fourth spoke? Just create another VNet and 2 more peering connections. The existing spokes are unaffected. With the NVAs deployed and peering established, we can now safely associate the remaining route tables with the hub subnets. Trying to do this earlier would have created black holes, but now the next hop IPs exist and can forward traffic. We'll start by associating the firewall route table with the firewall subnet. This tells the firewall NVIA where to send traffic after it's been inspected. Remember, this route table forwards everything to the IDS at 10.1.3.4. Next, we associate the IDS route table with the IDS subnet. This route table contains the most complex routing logic, with different next hops based on the destination. For example, spoke traffic uses VNet local, on-premises traffic uses the virtual network gateway, and internet traffic uses the firewall's external interface. Finally, we associate the management route table with the management subnet. This provides direct internet access for management tools, while still routing internal traffic through our security stack. The order of operations is important here. I always associate from the end of the chain backward, starting with the IDS, and then the firewall. This approach prevents any temporary state where traffic might bypass security because of a partial configuration. After these associations are made, our service chain is complete. Traffic from the spokes will hit their route table, go to the firewall, then to the IDS, and finally to its destination. The return path follows that same chain in reverse. Here's a subtle but important point. The gateway subnet still has no route table associated with it, because Azure doesn't allow it. This is by design. The gateway subnet has special routing requirements that Azure manages automatically. Now, let's verify that everything is working correctly by running some traffic tests. Now for the moment of truth. Testing our service chain. I'll show you several ways to verify that traffic is flowing correctly through both NVAs. These techniques are invaluable for troubleshooting production issues. First, deploy a test virtual machine in Spoke 1. This virtual machine will generate traffic to test our chain. A small B2S size is sufficient. The key is to place it in a subnet that has our Spoke route table associated. Using the Next Hop feature in Azure Network Watcher, we can see exactly where traffic will be routed. For a virtual machine in Spoke 1 trying to reach Spoke 2, Next Hop should show the firewall's IP address of 10.1.2.4. This confirms our route table is working. The IP flow verify test goes deeper, checking if NSG rules allow the traffic. This tests the complete path, including security rules. If this test fails but Next Hop succeeds, it means you have an NSG blocking the traffic. On the NVAs themselves, TCP dump is your best friend. For example, running a TCP dump on the firewall's ETH0 interface and filtering for the host at 10.2.1.4 will show packets arriving from your test virtual machine. You should see packets arrive on the firewall and then appear on the IDS, which proves the chain is working. The Connection Troubleshoot tool provides an end-to-end test, attempting actual connectivity and reporting where failures occur. This is particularly useful for complex chains where multiple issues might exist. If traffic isn't flowing, check the following in order: the effective routes on the source virtual machine, NSG rules on the source and destination, IP forwarding on the NVAs, and the peering status. This methodical approach will help you quickly isolate any issues. Remember that the first packet through a new flow might be slower as the connection state is established. Subsequent packets should flow quickly. Summary and next steps. Congratulations! You've built a functional service chain. Traffic from any spoke now flows through both the firewall and the IDS/IPS before reaching its destination. This provides enterprise-grade security inspection for all east-west traffic. Let's recap what we accomplished. We deployed 2 networked virtual appliances with static IPs matching our route tables. We enabled IP forwarding at both the Azure and OS levels, which is crucial for traffic forwarding. We established VNet peering between the hub and all spokes with forwarded traffic enabled. We associated the remaining route tables with the hub subnets, completing the routing configuration. Finally, we tested the chain using Network Watcher and packet captures, proving that traffic flows correctly. The service chain now works for inter-spoke traffic. A virtual machine in Spoke 1 reaching Spoke 2 traverses from Spoke 1 to the firewall, to the IDS, and finally to Spoke 2. Return traffic follows the reverse path, ensuring symmetric routing for stateful inspection. What's still missing? Connectivity to on-premises networks and the Internet. That requires a VPN gateway and gateway transit configuration, which we'll tackle in Part 4. We'll also configure NAT on the firewall for Internet egress. In Part 4, we'll add the VPN gateway, configure gateway transit, establish on-premises connectivity, and enable internet egress through the firewall. Part 5 will cover monitoring, troubleshooting, and optimization techniques. The hardest part is done. The service chain is operational. Next time, we'll add hybrid connectivity to complete the architecture. Thank you for your attendance. Please consider subscribing to the channel.